Let's put this all together and talk about how to graph rational functions. One thing to note is that for our vertical, horizontal, and slant asymptotes, although they're not part of the function, they're worth including because they tell the reader what the function is getting closer and closer to. That means that when we graph them, we can either graph them in a different color or with dashed lines so that the viewer can see that they're part of the graph, but they're not actually part of the equation. Let's go ahead and take a look at this example where g of x is x minus 1 times x plus 3 divided by x minus 2. As usual, we'll start by finding the x-intercepts by setting the function equals 0. Multiplying both sides by x minus 2 gives x minus 1 times x plus 3 equals 0, meaning we have two solutions, x minus 1 equals 0 or x plus 3 equals 0, telling us that x equals 1 or x equals negative 3. We can go ahead and plot those on our graph, x equals 1 and x equals minus 3. Similarly, we can look at the y-intercept by evaluating g of 0, that's 0 minus 1 times 0 plus 3, divided by 0 minus 2, giving us negative 1 times 3, divided by negative 2. That is 3 over 2, or 1.5, which we can again graph on our axes. Next, we'll look for vertical asymptotes. To find our vertical asymptote, we'll point out that there are no terms in the numerator that cancel with the denominator, and therefore we can just set the denominator equal to 0, giving us a vertical asymptote of x equals 2. Once again, we can put that on the graph with a dotted line or a different colored line. I did both, and I'm going to put this going all the way up. Lastly, we care about the horizontal asymptotes, and we'll notice that since the degree of the numerator is 2 and the degree of the denominator is 1, the numerator is 1 degree bigger than the denominator, so we don't have a horizontal asymptote, but rather a slant asymptote. In order to find it, we need to expand the numerator, x minus 1 times x plus 3. That gives us x squared minus x plus 3x. That's 2x minus 3. And we can set this up in our synthetic division with 1x squared plus 2x minus 3. Since we're dividing by x minus 2, we will put 2 on the outside. As usual, we bring down the 1. 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is 8. And negative 3 plus 8 is negative 5. This gives us a slant asymptote of 1x plus 4 with a remainder of 5. 1x plus 4, that's a line going through a y-intercept of 4 and extending off in both directions just like this. And now we can use everything that we've done in order to plot our actual function. We notice that near the origin, our function goes through the 3 points we've already drawn, and then we'll get arbitrarily close to both our vertical and slant asymptote. In order to figure out what's going on to the right of 4, we just need to plug in any point bigger than 4, let's say 5. G of 5 equals, sorry, my bad. We can plug in any point bigger than 2. So let's do 3, although 5 would work. 3 minus 1, 3 plus 3, divided by 3 minus 2. That's 2 times 6 over 1, or way up here at 12, which is around here. We'll notice that since we're restricted by both our vertical and horizontal asymptotes, we're not going to cross them, we'll just get arbitrarily close to them, and we'll notice that our function is symmetrical about this point here. In class, we're going to talk about how to graph the other side in a little more detail. We'll work on practicing graphing rationals, and we'll talk about how to solve rational inequalities and word problems. We will talk about what happens when all of this isn't enough information. We'll practice graphing rational functions, and we will solve rational inequalities with word problems.